Hello, everybody. Welcome back. Today we're going to be looking at Unit 7.11, which is the Introduction to Solubility Equilibrium. It's taking some of the same concepts we've been working with, but applying it in a slightly different setting. We're going to be doing a lot of calculating today, so have your calculators at the ready, and let's get started. All right, so as I said, we're going to be looking at equilibrium, of course. We're in the equilibrium chapter. But in the context of a solid dissolving into its aqueous components. Okay, and typically, guys, we're going to be looking at solids that, according to our solubility rules, would be considered either insoluble or slightly soluble. These are solids that hardly break down into their aqueous components at all. Okay, like for example here. And we're going to be looking at a special type of equilibrium constant. It's still an equilibrium constant, just like any other. So you have that capital K, but you have the little letters SP there. SP stands for solubility product. All that means is that this is an equilibrium constant connected to the situation of a solid dissolving. That's all it means. It's going to be set up exactly the same way, products over reactants. And I want you to look at this equilibrium expression that we've got here for this particular reaction. And you might say, well, wait a second, you just said products over reactants. Where are the reactants? Well, remember, guys, in equilibrium expressions, we do not include solids. All right, we also don't include liquids, but we're not dealing with that here. So the solid is always excluded. So a KSP expression, ladies and gentlemen, is always going to look like this. It's always going to be able to be written in one line because a KSP is specifically for a solid dissolving, and the solid will always be excluded. Okay, but we of course still use the coefficients as exponents. So what things might you be asked to solve for? Well, one of the things that comes up frequently in a KSP problem is solving for solubility. Okay, now what do I mean by that? Well, solubility is going to be defined as the concentration of whatever solid we're talking about. So in that example from the previous slide, bismuth sulfide. Okay, and notice the word concentration is there. All right, concentration, molarity, solubility, which you'll be asked to solve for sometimes, has the same units as molarity. Okay. And we're going to set these problems up very similar to the way that we were doing before with those ice tables, except instead of using the variable x, we're going to use the variable s. Okay, they represent the same thing. Okay, but it just helps us distinguish that this is a KSP problem. This isn't a typical ordinary equilibrium problem, but they represent the same thing. So S is going to represent the solubility of the solid, which is going to have the same units as molarity, moles per liter. Okay, of course, KSP is always going to be constant unless you change the temperature, just like any other K, but the solubility is variable, okay, and that's meaning it can change. And that's going to be especially true when we start talking about a concept called common ion effect. That comes in a later unit. So let's look at a sample problem. We're going to do number 1 together, and then I'm going to have you do number 2 on your own, okay? It says the solubility of bismuth iodide is blah, 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 blah. Calculate the KSP value. All right, well, I want you all to get in the habit, just like we have with many of our equilibrium problems. The first thing that I want you to do is to write out the reaction. Okay, and in this case, bismuth iodide is going to break down into bismuth the ion and iodide. Let's make sure it's balanced. I know we haven't had to, worry about that too much, but we've got to always make sure that it's balanced. Okay. And in this case, this type of problem, we are given the solubility value. So that is S. And again, notice the units. Okay, they're the same as molarity. And they want us to calculate the KSP value. Well, I'm going to set up a very tiny little ice table here. I'm going to squiggle through this column because it's a solid, ladies and gentlemen. Not going to be included in my KSP expression, so who cares? We don't care about it. Before the solid has dissolved, initially, there is no product, okay? So initially, all we have is the solid, all right? C, of course, in ice means change. And instead of using X, I'm going to use S. Now watch. Plus S, this one, plus 3S. Because remember, coefficients make a difference. So I've got S and 3S. All right. And then let's think about, sorry, this is getting so squunched up here, what our KSP expression is going to look like. I'll write that up here. KSP equals the bismuth iodide, or excuse me, the bismuth ion times iodide, and that's going to be cubed. All right. Now, if I plug these values there, well, they're not really values, okay, into that KSP expression, here's what it's going to look like. Bismuth's molarity is represented as S, and iodide, it's right here, is 3S, and it's raised to the third power. Okay, you have to do that sort of twice. My students often mistake that and they say, well, why do you have to deal with the 3 twice? Well, we had it here because of stoichiometry, and we have it here because that's how you write a K expression. So you do have to take care of it twice. All right, and we are supposed to solve, they want us to find a value for KSP. This is my unknown. Well, ladies and gentlemen, this number right here, that is S. Okay, so if we plug that number in for S, and be careful of your order of operations here. You've got to take that number and multiply it times 3, and then raise it to the third power. And then we're going to multiply it one more time for bismuth. Okay, so please understand, guys, all I am doing is taking this number and plugging it in right there and right there. Okay, and when I do that, here's my final answer for KSP. Let's go to 3 significant figures. So that would be 8.20 times 10 to the negative 19th. Final answer. Okay, so, this isn't that different, okay, than what we've done. It just seems really different, okay? So in this particular case, we were given the solubility. Remember, solubility is your value for S. Okay, we set up an ice table. We don't care about the solid, all right? The 2 ions are initially starting at 0. All right, you set up your ice table and then set up your KSP expression and plug that solubility in anywhere that you see the letter S. Okay, I'm sorry that was so squunched up and a little bit messy. All right, so what I want you to do is to pause the video and try this one on your own. It is the same exact setup, just with a different compound. So you try it. Okay, let's see how you did. So this one was the exact same setup where we were given the solubility of the solid. So that number in the problem, 2.05 times 10 to the negative 7th, that is the value for S. And we are supposed to calculate KSP. So I tried to write this out a little bit more neatly. Okay, so we've got the ice table here. Remember, I wrote out my balanced equation, filled in my ice table, and then wrote out my KSP expression and substituted 3S and 2S into that expression. And guys, you've got to be careful. It's 3S with parentheses around it cubed, okay? A lot of students just forget that set of parentheses and, right here would just write 3S cubed and 2S squared, when really, like this last part, for example, right here, if you were to simplify this, would be 4S squared. So just be real careful about that. So then on this line, I substituted in that solubility value that I was given. I just substituted it in anywhere that I saw the letter S, and this is my final answer. And guys, look at that number for KSP. That is a really, really small number. Okay, and again, if you look at your solubility rules, calcium phosphate, the solubility rules would say that's an insoluble compound. Well, this is why. Look at that KSP value. The forward reaction is not favored at all. The process of it breaking down into its aqueous components is not favored. And we can clearly see that by how small the K value is. So let's look at another situation. What if you're going the other way? Okay, this time we are given the KSP value and we are supposed to solve for S, the solubility. The setup is going to be exactly the same, it's just that our unknown is going to be in a different place. Okay, so I'm going to move over to a blank screen so we can write this, so I can write this a little bit more neatly. So the first thing that I always do is I write out the balanced reaction of how does this solid break down into its lead ion and 2 bromide ions, okay? I set up my ice table. We don't care about the solid. 0, 0, this will be plus S, this will be plus 2S. Okay, let's set up our KSP expression, which is going to look like this, with the lead ion and then the bromide, which is going to be squared. And if I substitute in what I found from my ice table, it's going to be S times 2S squared. And guys, can you all see that if I simplify that a little bit, combine like terms, then I'm going to get that. Okay. Now, if we come back to the problem, we were given the value for the KSP, 4.6 times 10 to the negative 6th. And that is equal to 4S cubed. Okay? If you do a little algebra here, and I'll do this with you, okay? We're going to divide by 4, both sides by 4, and then I'm going to take the cube root of that number, and that is going to give me a value for S, that's solubility. And let's go to 2 significant figures, so that gives me 0.010. And that, ladies and gentlemen, remember, has the same units as molarity, okay? And that's my answer. Okay, so this time we were given the KSP value and we were asked to solve for the solubility. The setup is exactly the same. It's your unknown is just in a different place. That's all. All right, so I want you to pause the video and try this second one on your own. Same setup, you try. Okay, let's check your answer to this second question. So I set up my ice table, I set up my KSP expression, solved for S, and I get 1.3 times 10 to the negative fourth moles per liter. Okay, so these problems are really not that challenging. It's just, it's in a different context, so it can seem it can seem a little unfamiliar. So these would be likely in free response. So what would a multiple choice question look like? All right, well, here's an example. I want you to pause your video and try it. All right, so I'm hoping that you set up an ice table for yourself, okay, which I did. And I wrote out my KSP expression and I substituted in 3S and 2S, okay? Now be careful, I know this seems like, silly, but a lot of students get 3 cubed incorrect, okay? 3 raised to the third power is not 9, okay? It's 27. So that's 27S to the third times 4S squared. Okay, if you can do a little mental math in your head, 4 times 27 is 108. And that'll be times S to the fifth. So if you were to isolate S, you would need to say KSP divided by 108 and take the fifth root of that answer. So letter D is our answer right there. Okay, so you didn't have to do very much number crunching. Okay, remember, this is multiple choice. You would not have a calculator. So this is something you could handle without a calculator, hopefully. All right, same setup. Now, another question that you might be asked is, given 2 different salts, which one is more soluble? Okay, now in KSP situations, guys, we are typically looking at salts that are not very soluble, but they might say which one is slightly more soluble, okay? In some cases, you can simply compare the KSP values, okay? And if that is the case, the larger the KSP value, the more soluble that salt is. But there's a problem here. Can you always just compare the KSP values? No, you can't. Look at that first bullet. It says you can only do that if the solubilities fall apart into the same number of ions. Now, what do I mean by that? Well, if we look at some examples from the previous slide, for example, those previous problems we were doing, okay? One of the examples we looked at was lead bromide. This compound breaks down into 1 lead ion and 2 bromides. So that is 3 total ions. Okay, how about this one? This is silver carbonate. Silver carbonate breaks down into 2 silver ions and 1 carbonate ion. That is also 3 ions. So those 2 compounds, I could answer the question, which one is more soluble, by simply comparing their KSP values. Bigger KSP, the more soluble. But let's look at, for example, one of the other compounds we dealt with, bismuth iodide, which breaks down into 1 bismuth ion and 3 iodides. That's 4 ions. I cannot compare 2 compounds that fall apart into different number of ions by simply looking at their KSP values. So what do you do in that circumstance? You have to, quote, do the math. Now, I know that's a very cryptic thing to say. What the heck does she mean by that? Do the math means solve for the solubility and compare those numbers. Okay? So if they fall apart into different number of pieces, this would likely be a free response situation because you are going to have to do some number crunching. You would need to solve for S and compare those. The bigger the S value, the more soluble it is. Okay. So sometimes multiple choice questions will give you this situation where you're comparing solids that break down into the same number of ions. They put it in multiple choice because you don't need to do any math. You can just compare the KSPs. All right, now, on occasion, you'll see questions that will give you some circumstances, give you some numbers, and say, will a precipitate form when we mix these two solutions together? And this is what, the formation of a precipitate might look like. You pour two aqueous solutions together and your solution turns cloudy, or you see something like this. That is the formation of a solid. And if you let it sit for some time, it would settle to the bottom of the beaker, and we could collect it through filtration maybe. But the point is, you have to be able to look at numbers and identify whether a precipitate will form, yes or no. And the way you're going to do that is using something we're familiar with, calculating Q, okay? We've seen Q before. Remember, Q is sometimes called the reaction quotient. Sometimes it's called the ion product. It doesn't matter what it's called. Remember that Q is set up exactly the same way as K, and in this case, KSP, but the molarities will not be molarities at equilibrium. They'll be in usually initial conditions. So how do you know if a precipitate forms or not? Well, it's real simple. If the Q ends up being a value greater than KSP, the answer is yes, we will get a precipitate. If it's less than, no, we won't. If it's equal, we say that the system is at equilibrium. Okay, so let's look at an example problem on how do you calculate Q. Okay, so I'm going to work this one with you. We'll do an example problem in just a minute for you on your own. So it says a solution is prepared by adding a certain amount of potassium oxalate to a certain amount of barium bromide. And then they give us a KSP for barium oxalate. So that's our big clue. Oh, that must be the precipitate that they're going to be talking about. Describe the appearance of the final solution. Use calculations to support your answer. What I'm essentially asking you here, guys, is there going to be a precipitate, yes or no? All right. So there's a big clue here. The fact that they have given us a KSP value for barium oxalate tells me that that's the compound that I care about. So just like any other KSP problems, I want you guys to get in the habit of writing out the KSP reaction for that compound that we're focusing our attention on. Okay? And the Q expression, guys, is going to look exactly the same as the KSP expression looks like. All right. The tricky part here is, how do I get those molarities? And you might say, well, that doesn't seem tricky. Where is barium coming from? It's coming from here. And you might say, well, there's the molarity for barium. No, not quite. That is the molarity of barium bromide before those two solutions were mixed. Okay. We are concerned with what is the molarity of barium at the moment that these two solutions have been mixed. Okay. So what we're going to do is we're going to use M1V1 equals M2V2. Why am I able to use that equation? Because we're adding volumes together. We're adding two different solutions together. They are going to become diluted, so I can do that. All right, so let's look at this information for the barium ion. All right, so M1V1 equals M2V2. My M1, my initial molarity of barium, is 0.25 molar. The initial volume was 0.15 liters. I don't know the new molarity, but the new volume is these two things mixed together. All right, so what is the total new volume when everything's mixed together? That's going to be 0.25 liter. And if we do the math on that, 0.25 times 0.15 divided by 0.25, I'm going to get that. So we're going to put that right here. All right, we're going to do the same thing for the oxalate ion. Okay, this time we're going to focus our attention right here because that's the information that is tied to the oxalate. Okay, we're going to do the same M1V1 equals M2V2. So the initial molarity is 0.2. The initial volume is 0.1. I don't know the final molarity yet, but when I mix everything together, I get 0.25 liters. And let's see what that gives us. .08. Okay, so let's put this in the calculator. Let's see what we get. So Q is equal to 0.012. And let's compare that to our KSP. And I can see that this Q value that I have right here is much larger, much larger than the KSP value. And if you look back on the previous slide, if Q is greater than K, we are make sure I spell it right. We are going to get a precipitate. Okay, and that's what you'll be asked to show. This would be a free response question. Show calculations to indicate how do you know if a precipitate will form, yes or no. Okay, they have to give you the KSP value, and that's the whatever compound they give you the KSP value for, that's the compound you want to focus your attention on. And start here. Write that equation. Write out the reaction for how it breaks down. Write out your Q expression, and then do your M1V1 equals M2V2 to find the molarities of each one. And I'm going to give you a chance to practice with that in just a second. All right, so this question is going to pull everything together that we have talked about. All right, we are given two salts. We're given the KSP value for one of them. We're not given the other, which means we're probably going to have to solve for it at some point. And there are 3 questions related to this. So I want you to read these problems very, very carefully. See if you can do them on your own, but I'm going to also talk you through it. All right, I know this was a lot, so let's take each question one at a time. So the first question says, a saturated solution of tin 2 hydroxide has a hydroxide ion concentration of 2.2 times 10 to the negative 9th molar. Calculate the KSP. Well, guys, I'm going to set this up just like all other KSP problems. I'm going to write out my reaction of how does tin 2 hydroxide fall apart. I'm going to set up an ice table. Then let's go from there. All right, so I've set up my ice table, I've set up my KSP expression, and I have set up, substituted in S and 2S. Okay, none of that should be surprising. Now, where did these numbers down here, where did those come from? Well, guys, in the problem, they told us not the solubility value for tin hydroxide. They gave us the molarity, which you can use as solubility, for the hydroxide ion. And look, that is right here. So I substituted the number that they gave us right there because they told me the hydroxide concentration. Now come over here. If I know that 2S is equal to this number, because this is the molarity of OH minus, the molarity for tin must be half that, because tin has a value of just S, not 2S. So I cut this number in half, and then I substituted them in, and I solved for the value of KSP. That problem was a little bit different because usually we are just given the value for S, which is the solubility of the solid, okay, of this tin hydroxide, and you can just substitute that in anywhere that you see for S. This problem was a little different because they gave us, instead of giving us the value for S, they gave us the molarity of one of the pieces, which was equal to 2S. Okay, so that was a little bit tricky. Okay, let's look at number 2. Would a saturated solution of chromium hydroxide have a higher or lower concentration of hydroxide than tin? Okay, hydroxide. So we know the hydroxide concentration from number 1, okay, the concentration coming out of tin hydroxide. So the emphasis here is, or the implication here is that we're going to have to solve for the hydroxide concentration in chromium hydroxide. But you'll notice, look, move your eyes up, we have the KSP value for that compound. So we're going to set this up just like we do all the others. Okay, this was number 1. Here's number 2. All right, I've got my ice table. I've set up my KSP expression. All right, we were given the KSP value, so I was able to solve for S. And that's wonderful, but what they wanted was the molarity of the hydroxide ion, which isn't equal to S, it's equal to 3S. So I took my value for S and I substituted it in right there. So 3 times that number gives me this. And then I compared it to the number given to us in number 1. And my answer here for coming out of chromium hydroxide has a higher value. It's a higher hydroxide concentration than the tin hydroxide. Okay, so this one gave me 3.7 times 10 to the negative 8th. Look at this one, 2.2 times 10 to the negative 9th. Okay, my answer for this one is a larger number than the one for tin hydroxide. So that answered that question. Okay, last part. Solutions of chromium nitrate and potassium hydroxide are mixed. And then it gives us some information. It says, will a precipitate form? Remember, guys, this is where you need to calculate Q and compare it to KSP. Now, you might be saying, well, usually they give us the KSP right in the problem, so I know which compound to be focusing my attention on. Well, if you look at these two reactants that are being mixed, chromium nitrate and potassium hydroxide, and think about what are the possible products, predict your products. We would have potassium nitrate, which hopefully you're remembering your solubility rules. That's got an alkali metal in it and a nitrate. That is definitely a soluble compound. That's not going to be the precipitate. The other product, chromium hydroxide, is an insoluble compound. And look up, move your eyes up in this problem. We have the KSP value for that. So in number 3, the precipitate that they're asking us to predict is chromium hydroxide. Okay, and this problem is especially nice because we don't have to do the whole M1V1 equals M2V2 thing. And look at what they've given us. The final molarity, meaning after these two things have been mixed, I can get my chromium molarity out of here, and I don't even have to do M1V1 equals M2V2. They are giving it to me. They're being very kind. And the final molarity, I can get my hydroxide molarity from here. So let's see. So as I said, chromium hydroxide is the one that we're concerned with. I wrote my Q expression, and I just took those molarities right out of the problem that they gave us. In the practice problem that I worked through with you earlier, we were not given the final molarities. We had to calculate it by doing M1V1 equals M2V2. But in this problem, they gave us the final molarities. How kind. I plugged them into my Q expression, solved for Q, found that Q was less than KSP. That's a smaller number. When Q is less than KSP, you will not get any precipitate there. Okay. Whew. Okay, so that was a lot, all right? And it seems like a lot of new concepts. It's really not, but it seems new because it's in a new context with solids dissolving. So I hope you have learned a little something in this lesson today, and I look forward to seeing you next time.